Today, I present our paper, AutoFHE. First, I want to introduce the secure deep learning under fully homomorphic encryption. So now we know a lot of companies, the cloud servers, they provide the machine learning servers, deep learning servers to customers. So when the customer wants to use machine learning servers provided by the cloud servers, they need to share their encrypted data. After the cloud server receives the encrypted data, first, the cloud server should decrypt the encrypted data, get plain text data, and then use deep neural networks to process the data and get the plain text result, and encrypt it again and send it back to the customer. During this procedure, we say the cloud server can see the data and the prediction result. So it raises privacy concerns. Sometimes the customers, they don't want the cloud server see their data and the result, but the cloud customers still wants to use deep learning servers provided by the cloud server. And fully homomorphic encryption provides a solution for this situation. So the customer just share the encrypted data under fully homomorphic encryption, and the cloud use the neural networks to process the encrypted data without decrypting it and get the encrypted result. So during this procedure, we say only the customer holds the secret key, and only the customer can see the data and the result. At the same time, the cloud server holds the pre-trained weights, so it can also protect the property of the cloud server. This is a simple history of the secure computation under the fully homomorphic encryption. The original idea was introduced more than half a century ago, but 15 years ago, it was first demonstrated. And the CKKS will, in this paper, we use CKKS. CKKS can encrypt the real number and the complex numbers. So CKKS is suitable for the computer neural networks. And bootstrapping can refresh zero-level ciphertext. We know the deep neural networks, they have a lot of layers, so it needs a lot of computations. So bootstrapping is necessary for the deep neural networks. And the MPCN first demonstrated the deep convolutional neural networks under RNS-CKKS FHE. But the MPCN, they use high-degree composite polynomials. The performance is very good, but the problem is that they use high-degree polynomials, so they use a lot of levels. So they need to call the bootstrapping operations many times, so it makes the latency is very, very high. To address this problem, we propose AutoFHE. This is the architecture of convolutional neural networks. So if we want to evaluate a convolutional neural network under fully homomorphic encryption, the input data, the input image and output predictions, they are encrypted now. We know the homomorphic encryption only supports multiplication, addition, and rotation. So it's okay to directly evaluate batch norm and convolution under fully homomorphic encryption, but it doesn't support some nonlinear activation functions like ReLU. ReLU is popularly used in convolutional neural networks. So we need to use polynomials to approximate the ReLU. So it's straightforward. If we use high-degree polynomial, we can precisely approximate the ReLU. But the problem is that if we use high-degree polynomial, we will use a lot of multiplications. In that case, we will use a lot of bootstrapping. So if we run out of all multiplications, we need to call the bootstrapping to refresh the ciphertext. And we know the bootstrapping is the latency is very high, and it needs a lot of memory footprint. So actually, the bootstrapping is a computational bottleneck when we evaluate neural networks under fully homomorphic encryption. So when we design a polynomial convolutional neural networks under fully homomorphic encryption, we should consider the secure requirement, inference latency, and the prediction accuracy. These requirements are provided by the customers. So security and inference latency, we need to choose appropriate cryptographic parameters. And when we design the convolutional neural networks, it will affect latency and accuracy. we need to carefully design the packing under FHE and the polynomials, number of layers, and the input image resolutions. So the design between the homomorphic encryption and machine learning, they are interactive to each other. So this is example of the existing work, MPCN. So input ciphertext level is 2, goes through convolution batch norm, the level is 0, and then call bootstrapping, and then use high degree polynomials. They just need to repeat these blocks. They can build the whole neural networks. Their performance is good, but the problem is this is a fixed architecture. Okay, you need to manually design architecture given any networks, and they need to periodically cause the bootstrapping, and the latency is very high. Okay, this is an example of use high degree polynomials. Intuitively, we can also use some low degree polynomials manually design. Okay, so you can imagine there is a lot of solutions between the high degree polynomials and the low degree polynomials. How can we get these solutions automatically? We can't manually design all of them by our hand. So our solution is that now the existing works, they are optimizing the polynomial functions. They design different polynomial functions, and then manually design the whole architectures. We directly optimize the end-to-end polynomial neural architectures. So first, different layers, they have different polynomials, high degree or low degree. And now we need to consider where to cause bootstrapping. So we need to optimize the bootstrapping and the polynomials at the same time. Why we need to optimize the end-to-end polynomial architectures? Because it can generate different solutions over the trade-off between the latency and the accuracy. So it can satisfy the different requirements in the real world. Sometimes the customers, they want faster response, so we can give them solution 1. Sometimes the customers, they say, I can wait for accurate result, so we can give them the solution 3. So AutoFHE is conducted on the cloud server side, and after given any kind of neural networks, it automatically generates different polynomial solutions. These solutions, they are distributed over the trade-off between the accuracy and the latency. And customers, they just need to provide their encrypted data and their request. This is our definition of the evil ReLU. We call it evil ReLU. It's a polynomial ReLU. It has degree 1, degree 2. Degree 1, degree 2, they are widely used in previous work. It's pruning and quadratic. And we also use high degree approximation. And when we optimize the high degree composite polynomial, we didn't use interpretation theory to get the coefficients. We use differentiable evolution to search their coefficients. And we know when we training our neural networks, so the challenge is that when we train polynomial neural networks, the training is not stable. It has a numerical problem. Some small numbers may be amplified to very big numbers. So we propose this in backpropagation to make the training more stable. So now, how to optimize end-to-end polynomial neural architectures? We use a multi-objective evolutionary optimization. So different layers it's possible to use different polynomials, high degree or low degree, because we know the different layers, they have different sensitivity to the approximation. And we need to consider how to appropriately to cause the bootstrapping. So this is a joint search problem. So we transfer it to a multi-optimization problem. So it can give us a flexible architecture, and the bootstrapping is on demand. Why we need to optimize both objective accuracy and latency? If only optimize one objective, it can give us only one solutions. But if we optimize accuracy and latency, it can give us the different solutions on the Pareto front, and we don't need to tune the weights, and these solutions are Pareto optimal. However, we say some existing works, they just minimize the degree or minimize the depth of polynomials, but it not necessarily reduce the number of bootstrappings. So we need to directly minimize the number of bootstrappings because the bootstrappings dominate the latency when we evaluate convolutional neural networks. So this is an evolutionary multi-objective optimization. We have different solutions, and it's like a natural selection. We exchange different solutions to generate new solutions. We mutate some solutions to explore the search space to see if we can find better solutions. And we just keep the Pareto front solutions. We repeat this generation until we meet our search budget. And we also fine-tuning the polynomial convolutional neural networks. We know the polynomial networks, their representation learning ability is not as good as ReLU networks. It was proved many years ago. So we inherit the trainable weights from the ReLU networks. And then we use KD transfer the knowledge, representation knowledge from the ReLU neural networks to the polynomial networks. We did experiments on the CIFAR, encrypted CIFAR dataset under RNS-CKKS. So in our experiments, we show our result. The AutoFHE has better trade-off between the accuracy and the latency. So this is the depth of layerwise evolutionary ReLU. So we say, they have different layers need the different precision of polynomials. So it can help us to design the polynomial networks under fully homomorphic encryption. This is a layerwise polynomial ReLU, the different functions. Okay, so let me conclude the presentation. So the takeaway is that we should optimize the whole polynomial architectures rather than design the single polynomial functions. If you can check, you can scan this QR code to see our paper code and other source. Thank you.